So do we have a chairman?
Oh,
Yeah.
are you expecting an introduction?
No, I just wanted to tell me to stop.
Oh, okay. I can do that.
So you all right, Steve? So, I'm going to talk about joint work with Alan. So I should write his name up. I guess everybody knows, it doesn't matter, does it, Alan? So it's joint work with Alan. And maybe I'll write my title up. So it's 0 free regions of multivariate Tutte polynomials. So I like interactive seminars. So please interrupt me and ask questions or make comments. So G is going to be a graph with vertex set V and edge set E, and it's going to have n vertices. So the multivariate Tutte polynomial of G, or the Potts model partition function, is defined as follows. So it's the sum over all subsets of the edge set of Q to the K here times the product E is in A of V of E, where Q and V, which is a set of edge weights, are indeterminates, and K of A is the number of components in the subgraph with vertex set V and edge set A. So I guess for the purpose of this talk, I'm going to think of Q and V as being real variables, and I'd like to find regions in the QV plane. I guess it's not a plane, but whatever it is. I'd like to find regions for which the multivariate Tutte polynomial has no zeros. I'd like to find regions where I know what the sign of this thing is.
And what is the motivation for 0 free regions?
Alan?
Well, I mean, anytime you have a polynomial, it makes sense to be interested in zeros.
Yes.
And if you have a zero free region, then you know it's not zero there.
Is that okay? So J is a graph. My graph J is separable if I can write it as the union of two subgraphs with so the vertex set of the first subgraph with the first subgraph and the second subgraph having at most one vertex in common and no edges in common. And I guess just to make sure it's not trivial, I'll want the edge sets to be non-empty. So it's known that if J is separable, then we can write the multivariate Tutte polynomial as a product. So if J is separable, then Zj of QV is Zj1 maybe I shouldn't write the independent. Well, I've written them now, but never mind. ZG1Q V1 times ZG2Q, let's call it V. So really it's V restricted to the edge sets of J1 and J2 if there are no vertices in common. And otherwise we divide by Q. So we'll get a Q to the minus 1 times ZJ1 times ZJ2. So a particular case of the multivariate Tutte polynomial is the Tutte polynomial where all the edge weights are equal and we have a kind of change of variables. And an even more particular case is where we put all the edge weights equal to minus 1 and then we get the chromatic polynomial. So the chromatic polynomial of J is ZJQ minus 1. So minus 1 everywhere. And it's known that so this is just a one variable polynomial. So it's known that we know some zero-free intervals on the real line for the chromatic polynomial. So the idea is we would like to extend these intervals to regions in the QV plane. So I'll draw it in the QV plane. It's not really a plane because this is a vector of different edge weights, but if everything's equal to minus 1, then we have 1 and 32 over 27. And by this result, we can assume that J is non-separable. So if we know what happens for non-separable graphs, we can work out what happens for all graphs. So let's assume that J is non-separable with n vertices. Then this is a 0, I guess. So here we know that well, let's write it as Z. So I'm really talking about the chromatic polynomial PG along the line where V is minus 1 everywhere. And we know that along this line, ZJ is times minus 1 to the n is greater than 0. And here we have minus 1 to the n minus 1 times Zj is greater than 0. And here we have minus 1 to the n times Zj is greater than 0. Maybe it would have been clearer if I'd wrote Pj's instead of Zj's, because that's what I mean. So by continuity, you would hope that you'd be able to move away from this line V equals minus 1. And so that's what myself and Alan have done. And it stems from the interval between 1 and 32 over 27, the fact that this is greater than 0 was something that I proved a long time ago. And not quite as long ago, but still a long time ago, myself and Alan came up with a simple proof. So my proof is quite a complicated graph theoretic argument of theirs. And we came up with a simple proof which just uses one graph theoretic lemma and some ugly analysis. And then well, you'll see from the picture that things kind of took off from there.
So this is true for any graph, right? For any graph G, these are 0. I mean, these inequalities are true, right?
Well, no, this is actually, so this is true. This is n minus the number of components, and this is n minus the number of components minus the number of blocks.
I see, because this is just for separable.
This is for non-separable graphs. Yeah.
And then is the 32 over 27 sharp?
Yeah, so on this line, Carsten showed that the zeros of the chromatic polynomials of graphs are dense after 32 over 27.
You can find graphs that have zeros there.
Yeah, in fact, that you can find them dense on
Yeah.
this line. So if you want to go beyond this, then you can't look at all graphs. You have to look at special families of graphs. So Dong's got a nice result that goes from all the way up to 2. And also for plane triangulations, you can go all the way up to 2. So this is something I prepared earlier. So this is our theorem. So non-separables become two connected here, but that's just because I have a bad memory. So it means the same thing. So the interval between minus infinity and minus 1 is spread out to fill the whole space between 0 and minus 2. So by this I mean that if we have ZJQV and all of the edge weights belong to this region, then the multivariate Tutte polynomial is non-zero with sign minus 1 to the n.
They have to be equal.
No, as long as they lie in this region.
Now, I mean, in the bit of the theorem to the right of q equals 0, I mean, you have some kind of precise analytic formula for this curve.
Yes.
Do you?
Yeah, in fact, hopefully before the end I'll tell you what it is.
And this boundary is sharp again.
In some sense, yes, but not in a very satisfactory sense. So we also have a conjecture. Here's the conjecture. So I should have said, so up here it's kind of trivial that the partition function, the multivariate polynomial is going to be positive, because if the q's and the b's are positive, then this thing's going to be positive. So this curve comes actually from a particular two connected graph with two vertices, which is this one. So if we look at the zeros of the multivariate Tutte polynomial of this graph, it'll tell us what these two curves are. And it also tells us what these two curves are, up to 9/8.
I have one question, but this either doesn't include a 9 when all of VE is equal to -1. For the chromatic polynomial, your inequality also true when all of VE equal to -1.
I think the -1, -2 maybe is not big enough.
Oh, so this is -1, and this is -2.
Oh, right.
Thanks, guy. Maybe I should put it to the side there.
Yeah.
But, so what we think is if you also put a bound on the number of edges in the two connected graph, then these intervals get bigger. So if we said that there were at least if it was G was a two connected graph with at least 3 edges, then it would rule out this example, and we think the curves move out. In fact, we can prove they move out. We get bigger intervals for 3 edges, for at least 3 edges, and bigger intervals for at least 4 edges.
Okay.
But-
It means actually the family, if the family is smaller, the bounds is the area is bigger. I mean,
Yeah, if we kind of rule out small examples, then the regions get bigger. And we think they tend to particular regions which are over here, which are called the diamond intervals. So I guess we're looking at it like this and thinking of these things as being intervals. for any particular Q. And so we think and so this is a particular it's a particular curve, and we think as the number of edges increases, the regions fill out and almost reach this curve. And of course, something funny must happen at 1 because the sign changes. So what we think happens at 1 is that they come in here and go out again. But it gets smaller and smaller as the number of edges increases. And these sections of the curve are the same as these sections of the curve. So we can prove our conjecture for Q at least 9/8. But smaller than 9/8, these small annoying examples come in.
And your conjecture is on any two kinetic graph, right?
Yeah.
And what is this?
So, I mean, to make this more precise, you would say if you have m edges, then you can find particular regions which depend on m. If you have at least m edges, there are particular regions which depend on m, and the limit as m tends to infinity of those regions are these things, which hopefully I'll be able to define before the end. So just to get warmed up, I'd like to start over here. So this is the kind of simplest oh dear, I can't bend down. Okay. So we're going to look at Q less than 0 to start off with. And we have the following theorem. So in fact, we don't need two connectivity for this theorem, we just need connectivity. So it's J, a connected graph. With n vertices. And I want to write the multivariate Tutte polynomial as, I want to group all the powers of Q together. So Zj QV is going to be the sum, oh, I guess it's K. K equals 1 to n of Q to the K times some function of J and K of V. So I'm gathering together all the terms in Q to the K and calling those C. So if I guess we'll have C J K of V is going to be the sum A contained in A, V A has K components of the product A is in A, V A. So then, minus 1 to the n times c, what's n minus 1, I guess? N minus k even, times c g k v is greater than 0 for all VE for VE in minus 2, 0 for all A in A. That makes sense. This is maybe it's better to be an F. So it's saying that the same thing happens as for the chromatic polynomial, that the coefficients are going to alternate in sign. If we write them as coefficients of each power of k, so because k is negative, that will imply that this thing is going to be positive for all q less than 0 and v in this interval.
I think you want loopless, don't you? Loops always make a mess.
Yeah. So
A loop at E brings in an overall factor 1 plus VE, and that could have either sign here.
yeah. So I kind of try to simplify everything by thinking of non-separable graphs. But then I thought, well, this holds for connected graphs, but it's actually connected loopless graphs.
So it's a little miracle that, I mean, this clearly works only when the v's are negative, right? This kind of argument. Then the alternation in sign proves that it's positive or non-zero. And is it a lucky break that the region ends at the x-axis, the shaded region on your picture above? Or maybe these two things are related somehow.
Well, if the V's are positive, then they all have the same sign.
Oh, that's true. That's true, yes. You're right. But there's I mean, in the northwestern quadrant, it's not trivial because Q, I mean, it's trivial if Q is also positive, right? But if Q is negative and the V's are positive, then it's not obvious that.
No. No.
Yeah.
You don't expect, because if the V's are all positive, then the C's are all positive.
Yeah.
And if the C's are all positive and Q is negative, then of course they could add up to 0.
That's right. So in principle, it could have been conceivable that the zero-free region extends.
We can't extend it. We can't extend this particular region because we can find zeros close to the boundary of this region.
For particular graphs.
For a particular graph.
I see.
Yeah.
Okay. Yeah. Okay.
But I agree with you that it would be nice to know more about what happens in the non-shaded regions. So
Yes.
a really wild conjecture would be that the zeros are dense in the non-shaded regions when you take V to be constant. So the proof of this is fairly straightforward. At least it should be. Except I've gone straight to case 2. What happened to case 1? Oh well. I wonder if I could rub that off. It's probably better to write here, huh? Oh, go down again. Oh, that's exactly what I didn't want to do. Okay. I hope you can cut that out, Steve. So we use induction. Oh dear. On the number of edges. So the first case is G is a tree. So I think I'm going to need my CGK back.
You mean the VA as data.
Thank you. If G is a tree, why is that? So I want to try and show that this is true. So I've got -1 to the n minus k times c gk is going to be -1 to the n minus k. So to get a subset of E with k components, we're just counting all subsets of E of size
Minus K.
n minus k. So this is just the sum is contained in A. The size of A is n minus k of the product E is in A VE. And now these are all negative, and so we have a -1 to the n minus k and a product of n minus k negative things. So this is greater than 0. So the second case is J has a pair of parallel edges. So there is, if we have parallel edges, then there is a lemma for reducing two parallel edges to one single edge. So we know what effect that has on the multivariate Tutte polynomial. So if this is G, and we have two edges with weights V1 and V2, then we can transform to a graph. Well, let's call this G minus E1. So the top edge is E1 and it's got weight V1, and the bottom edge is E2 and it's got weight V2. And so maybe I'll take away V2. Doesn't matter really. And the weight on this new edge, which is actually just going to be E1, is V1 plus V2 plus V1 V2. And then the lemma is going to tell us that Zg of Q V is the same as Z G minus A of Q V dashed, where V dashed, all the edges other than E1, E2 get the same weight, and E2 is deleted, and the weight of A1 is replaced by V1 plus V2 plus V1 V2. So now we just apply induction, and we use the fact that if V1 and V2 belong to -2, 0, then V1 plus V2 plus V1 V2 belongs to -2, 0. So we can apply induction to this graph, and the coefficients are the polynomials are the same. The coefficients are the same. The number of vertices is the same. So if this holds for G minus E, K and V dash, then it holds for G, K and V.
Can V be -2?
Sorry, Fan Lane?
No, V1, V2. Yeah, it cannot be -2, right? Not be equal to.
could V1 and V2 be equal to minus 2? I think if it was, then would this be 0? So we could allow the closed interval, and then we would get a greater than or equal to.
So this is again a convenient property of this interval, this little implication in the corner.
Yes.
Yeah.
We change it.
So in fact, this is really what makes it work. So this interval is closed under parallel reduction.
And again, it's tight at minus 2.
Yeah.
So that's it. That's a
The
convenient
easiest way-
accident, right?
The easiest way to think about parallel reduction is that 1 plus V multiplies. 1 plus V effective is 1 plus V1 times 1 plus V2. So in the variable 1 plus V, which multiplies, you're looking at the interval minus 1, 1. And minus 1, 1 is obviously closed under multiplication. That's the easiest way to think about it.
So the third case is when J has no parallel edges and is not a tray. So then we choose A in A, which belongs to a cycle in J, and we use the so this is the parallel reduction lemma. So we use the deletion contraction lemma. So the deletion contraction lemma tells us that Zj of Q of A is Zj minus A of Q of A plus VE times Zj of Zj contract A of Q of A. And I'm fudging things a bit, so this V is the same as this V, except E's disappeared. So here we delete the AG from J, and here we contract the AG in J. And so we apply induction to J minus A and J contract A. And we gather the terms together. And we need to make sure that we're stayed inside our family of connected loopless graphs. And because E is in a cycle, when we delete E, we're still connected. And certainly when we contract E, we're still connected. And we want to be loopless, so if we delete an edge, we can't create a loop.
The cycle is at least 3. If it's length
Yeah.
2, you're back in case in the previous
Yeah.
case.
So if we contract an edge and create a loop, then the cycle had length 2, and that was case 2. And here the number of n hasn't changed. Here n has gone down by 1, but we've got this multiplier outside which is negative. So this is not completely obvious because we're going from the polynomials to the coefficients, but if you work out the details, it goes through. So that's it. And so the graph, so it's in some sense best possible, and the graphs which show that it's in some sense best possible are little graphs again. So we have K2 joined by M edges. This is G. And so if G is this graph, then the multivariate Tutte polynomial of, and do I want to take all the edges equal to this? I guess I want to take all the edge weights to be the same. So this is Q times 1 plus 1 plus V to the M minus 1.
Q there,
There's a Q there somewhere.
first one.
First one's a Q. Thanks, Alan. So if V is close to if V is positive and small, then we can solve this for, so Q is negative. If V is positive and small, we can solve this for V and find 0. And similarly, if V is less than minus 2, and as M gets large, the zeros tend to 0 and minus 2. Great. So we go on to Q greater than 0. We have a kind of abstract theorem which we apply to get various results. One, two, three. 1, 2, 3, 4. Ah, there we go. So to state the abstract theorem, I'm going to need some more definitions. So we're going to use parallel reduction, which is dissipated, unfortunately. So if V1 and V2 belong to R, I want to let V1 parallel V2 be V1 plus V2 plus V1 V2. And so as for the parallel reduction lemma, there is also a series reduction lemma. So we say two edges are in series if they're incident to a vertex of degree 2. And this is V1, V2, and we will replace by one edge with weight, I can never remember this, V1, V2 over
Q plus V1 plus V2.
Q plus V1 plus V2. Thank you, Alan. So we'll let V1 series, and now series depends on Q, be that thing. So then we have, well, I guess we've already seen the parallel reduction lemma. So he is writing it out again in a slightly different way. So Z of is the same as Z of and the series reduction lemma is Z of now we get a prefactor of Q plus V1 plus V2 times the series reduction. And now some more notation. So if I have some subset of the rails, I'll let V parallel V be the set of all V1 parallel V2, where V1 and V2 belong to V, and V series V be defined similarly, so it's the set of all V1 series Q V2, where V1 and V2 belong to V. So as Mihai pointed out, the important thing for the Q less than 0 theorem was that the interval minus to 0 was closed under parallel connection. So here's the theorem. So suppose, I don't think Alan's going to like this, but never mind. Suppose M and is an integer, M greater or equal to 2 is an integer. Gamma is also an integer, which is going to be either 0 or 1. And Q is a real number, is a positive real number. I think I'd rather have a let here, sorry. So now I'd like to suppose. So suppose V contained in R, satisfies. So there's going to be 4 conditions. So the first thing is I want V to be contained in minus 2 minus Q over 2. Second thing I want is that V is closed under parallel connection. And then I'd like V to be closed under series connection. I'd like V to be closed under series connection. And then I'd like the multivariate Tutte polynomial evaluated at all small graphs for edge weights in V to have the right sign. So I would like minus 1 to the n minus 1 plus gamma times ZG QV to be greater than 0 for all 2 connected graphs J.
Is there a restriction on how big Q is?
Sorry?
And Q being,
In this abstract theorem, it can, but we'll say that the hypotheses actually imply that Q must be less than or equal to 32 over 27. So for all 2 connected graphs with n vertices and m edges and edge weights belonging to V. So that's the hypothesis.
So D is quite a strong assumption, right?
Yeah, it's good. It has to be a nice interval. I mean, it has to be a nice subset of R. Then the conclusion is that this holds. So this is for all graphs with n vertices and exactly m edges. The conclusion is that the same thing holds for all graphs with n vertices and at least m edges. So this is the base case of the induction. So the proof is almost as long as the statement, I think. Oh, it's short.
Similar to the previous one, right?
Yes, the proof is very similar. So the proof is induction on the size of A. So I'm assuming G is a two-connected graph with n vertices and at least m edges, and all the edge weights belong to my interval V. Then if the number of edges is actually equal to m, then it's true by D. So we suppose the number of edges is greater than m. So if J has a pair of parallel edges, then we apply the parallel reduction lemma. Parallel. God, I just spelled parallel, it's gone.
Yeah, so you assume the graph has no loops, right?
Yeah, so I'm assuming it's toe-connected. And by toe-connected, I mean non-separable. So. And so you have to check that the edge weights. So when we do use the parallel reduction lemma, we stay inside the interval because of this property. N doesn't change, gamma doesn't change. So we're happy. And use B and induction.
Yeah, what's comma is either 0 or 1. Okay.
Yeah. It's an abstract theorem. It's an abstract gamma. So if when we apply it, gamma is going to be 0 for q between 0 and 1, and gamma is going to be 1 for q between 1 and 32/27. So if J has a pair of series edges, then we apply the series reduction lemma, and we use A. We need A now because of the prefactor in the, I guess, series reduction lemma is gone. It's not very good planning. I should have rubbed these pictures off, I guess, but never mind. So if you remember, the series reduction has a prefactor, and for the prefactor to have the right sign, we want, I think, V to be contained in minus infinity minus q over 2. So that's where this comes from. So we can assume J has no parallel edges. Well, with graph theorists, at least some of us are. So J is simple, which means it has no loops and no parallel edges, and minimum degree So now we use the only the only bit of graph theory that's left in the 32/27 proof. So it's a graph theoretic lemma, which is probably known, but we haven't been able to find it in the literature. But it's very elementary. So if J, suppose J is non-separable, simple, and D of V is at least 3 for all V and B, then G has an edge E such that both J minus A and J contract A are non-separable. I'm jumping backwards and forwards between non-separable and co-connected, eh? Right.
They're not quite the same because of degenerate cases.
Yeah, so this is non-separable, but it's not co-connected.
And you're non-separable are allowed to have loops?
Non-separable, you don't have loops,
You don't.
and it's up to debate whether co-connected can have loops or not. So if J is simple and has minimum degree 3, we can find this nice edge that we can reduce both by deleting and by contracting. So now we can use the deletion contraction lemma. So choose E such that both J minus A and J contract A are two connected, and apply deletion contraction lemma. So because we have this toe connectivity in the hypothesis, we have to make sure that it stays toe connected when we use deletion and contraction. And in the deletion contraction lemma, for the deletion term, n stays the same and gamma stays the same, so the sign is okay. For the contraction term, n goes down by 1, but we multiply by the weight of the edge E. And because the edge E has negative weight, then the contraction term has the right sign as well. Is that okay? So it kind of means that in order to prove a theorem like this, all you need to do is check it on graphs with a few edges. So the first picture comes from m equals 2. So an almost immediate corollary of this is G is 2 connected. 0 is less than Q is less than 1. And VE belongs to minus Q minus root 1 minus Q plus root 1 minus Q for all A in E. Then minus 1 to the n minus 1 Zj QV is greater than 0.
Minus 1 plus or minus the square root?
Minus yes, it should be, huh? I've got Q written down here, but it should be 1. So Q comes in for Q greater than 1, eh? And the proof is we just take we take gamma equals 0 and m equals 2 in the theorem. So there's only one non-separable graph with 2 edges, so that's it. So we have to check that this interval is closed under parallel and series, satisfies this, and then check that this is true for that one graph.
Right. Here, then what's n? Because your result here n and the condition n is same, right? Condition 4 there is n vertices, and the final result also n vertices.
Yeah, so n can be anything.
No, I know, but n should be fixed for the whole result, right?
No. So we have to check it for all graphs. So m is the important parameter. So we take m equals 2.
Here we cannot just use m equal to 2. If m equal to 2, then n must be, n cannot be too big. N is too big, the graph is not too connected graph.
Yeah, so if m equals 2, this implies that n must be 2.
Yeah.
So to check D, we only have to check
okay, I
for
understand.
2 edges and 2 vertices. But then in the conclusion holds for graphs with an arbitrary number of vertices and edges. So so if you give us 2 minutes, I'd just like to show you where 32 over 27 comes from. So we've got stronger corollaries for m equal to 3 and m equals 4. So we've shown that just by checking small graphs, we've been able to make the region between 0, Q between 0 and 1 a bit bigger than this, a bit bigger than this. So to try and show you where 32 over 27 comes from, so we want to try and satisfy these. So these are the 2 important hypotheses, that V is closed under parallel and series. So let's suppose Q is greater than 0, and if it satisfies, and we have some interval V, and if it satisfies B and C, then we must have V series V parallel V series V contained in B. And in particular, if V belongs to V, then V, maybe I should have just wrote this down. So if it's closed under parallel and series, then it's closed under this combined operation, and in particular any element is closed under this combined operation. So we can actually work out what the value of this thing is. Maybe it's not so interesting what it is. So let's call this diamond Q of V. So the diamond notation is because it's kind of a, if you imagine that we were reducing this kind of configuration inside the graph, then you would do a series on V and a series on V and then a parallel on the two series. And we would get theirs. So what we do is we look at the fixed points of this map. So we solve diamond Q of V is equal to V, and that implies that V cubed minus 2QV minus Q squared is 0. So we get this cubic. Now, this cubic has one real root, so it's a cubic in V. It has one real root if Q is less than 0, or Q is greater than 32 over 27, and three real roots V diamond 1 of Q, which is greater than 0, which is greater than V diamond 2 of Q, which is greater than or equal to V diamond 3 of Q, which is greater than or equal to minus 1 for 0 less than Q less than or equal to 32 over 27. And the middle fixed point is an attractive fixed point. So we can use that in order to construct an interval satisfying these three properties. So this interval I diamond Q, which is up there, is this this middle root. So it's V diamond 2 of Q and Q over V diamond 2 of Q. So if we take this interval, we can show that it satisfies A, B, and C for Q between 0 and 32 over 27. And in fact, we can show the converse. We can show that any interval which satisfies A, B, and C, if there exists a non-empty interval which satisfies A, B, and C, then we must have Q between 0 and 32 over 27, and we must have V contained in the diamond interval. So then the theorem for Q between 1 and 32 over 27 comes from this abstract theorem, and these parts of the curve come from taking m equal to 2. So in order to satisfy D, we needed to hold for our favourite two-connected graph with two edges. So that gives one kind of constraint, which comes up here. But then we also need the interval to be closed under parallel and series. And that tells us it has to be contained in I diamond. So the I diamond constraint comes in here. And so we get this kind of funny shaped region. And the two curves meet at 9/8.
Are those cubic curves?
This is a quad. So the thing that comes from K2 is a quadratic. So this is minus Q plus or minus the square root of Q minus 1, I think. So the top one is the plus and the bottom one is the minus. And then this thing is I don't know if you'd say it was a cubic, would you? It's the thing that comes from this funny road. I'd like to stop there. Sorry for going on so long. Questions? More questions? Yeah?
Yeah, so how did you know that was the right combination? V series V parallel V series V, as opposed to V parallel V series V parallel V, or would that give the same thing?
I cheated a bit because I took interval. In order to simplify things, we're looking at intervals with the property that the leftmost endpoint is Q divided by the rightmost endpoint. And there is a duality in the weights. So if you have where does the duality come from? If you have a planar graph with weights, and you look at its planar dual, and you replace the weights in the primal by this operation in the dual, then the polynomial is the same up to prefactors. And duality interchanges parallel and series. So if we take a self-dual interval like this, it means that we only need to check parallel, and then we get series for free. And because this is self-dual, then it would be the same if we took parallel, series, parallel. So this kind of diamond thing came up in my graph theoretic proofs all over the place. I don't know. Do you remember why how we came up to the diamond interval?
Well, if you think about trying to satisfy B and C with a self-dual interval, you're inevitably led to one of those endpoints is a fixed point of the diamond construction. The diamond construction is series followed by parallel, right? But series and parallel are dual. So series followed by parallel is the same as series followed by duality followed by series followed by duality. So the diamond map is actually the square of series followed by duality. And so I think these are actually the fixed points of series followed by duality, if you want. I mean, if you try to satisfy B and C with the self-dual interval, you're led to the diamond construction. And of course, Bill was independently led to the diamond construction for his counterexamples.
Sorry, I should have said that the whole thing goes through for matroids. Right? I wanted to talk about graphs, but it's actually a result about matroids, and almost everything we've done goes through for matroids. It's just checking the small cases. There are more matroids than graphs once M gets. So I think the largest case we can only do for graphs, not matroids. But for matroids, we have the duality for everything, not just planar graphs. Thank you.